joining us for today's Würth Electronic webinar presented jointly with our friends over at Texas Instruments. Now, today's presentation is Power Up Your Design with the SN6507 Ready to Use Development Kit. And we are very, very excited about the advancements that this kit has made. Presenting today is Shinu Matthew, Application Engineer of Isolated Bias at Texas Instruments, and our very own Dean Humala, Senior Manager of Product Management at Würth Elektronik. Now, because you registered for today's webinar, you will automatically receive the long form video replay and the slides when they become available. You can simply look for that email coming from webinar team at we-online.com. So do make sure that that is whitelisted. It's webinar team at we-online.com. At the very end of this webinar, our presenters will be answering your questions in our live Q&A session. You can ask them in the chat. It's very simple and easy to use. So whenever you would like, you can test it out. I see we do have one comment right there. Hello, Christopher or Christoph. It's very nice to have you joining us today. We will try to get through all of the questions, but if your question does not get answered, or maybe we need to get some more technical help, then we'll call in some more assistance, but we'll make sure that we do reply back at webinar team at we-online.com. Now let's get into our presentation, Power Up Your Design with the SN6507 Ready to Use Development Kit, presented by Würth Elektronik and Texas Instruments.
Hello everyone, myself Shinu Matthew, Application Engineer, Texas Instruments. I just want to check my slides are visible. I hope my slides are visible, and yeah, so today we are discussing about the TI isolated bias supplies specifically for transformer driver application. If you see isolated bias architecture which is used in power stages, TI specifically have three types of isolated bias supplies. Basically, one is the flyback controller, which includes the 2518 series of devices. These are specifically the primary side regulated power supplies. And the other one is the push-pull and the LLC type of transformer drivers, what we have. Today, majorly, we are discussing on SN6507, the push-pull driver based on the transformer driver applications. And if you see the another type of the power stage, we have a distributed power stage that contains an integrated DC-DC modules, specifically the UCC 141 and 3-4 series right up to 2.5 watt of power the devices can deliver. So if you see the power stage architectures, specifically the isolated bias architectures, it is having three different form we can actually consider to use. One is the centralized architecture, where the power can be go up to 50 watts, which can be, it will be generated from a single power supply with multiple output windings, similar like a multi-output flyback system from a single transformer. And in semi-distributed, the high side will have individual isolated power supplies, and the bottom side will have a single driver which gets powering to maybe the 2 or 3 different gate drivers. So in the distributed, everything will be completely isolated. We'll have 4 or 6 individual power supplies which will be contributing to the gate driver power application. So if you see the generation of TI transformer drivers, so we have a series of devices which starts in SN. These are specifically the push-pull series of devices, starting from SN6501, which can work up to 5 volt of power with a switching frequency of 410 kilohertz, right? And it's a very small SOT 23 5-pin package, which it's very, very simple to use. And the next series is SN6505 series, which contains 2 versions, A and B, specifically with 2 different switching frequencies, 160 kilohertz and 400 kilohertz. And the maximum switch current device is capable up to 1.7 ampere. So the next series comes with SN6507. Here the input voltages can go up to 36 volt with an adjustable switching frequency starting from 100 kilohertz to 2 megahertz. And with an external clock synchronization, the device can go up to 4 megahertz of switching frequency. And the current limiting is adjustable, which can go up to 1.3 ampere of current. So the device is having additional features compared to the old generation devices, SN6501 and 05. It's having adjustable slew rate control, and the device is having spectrum clocking, which helps in the EMI. And the device will have adjustable soft start, UVLO, OVLO, and the device can work on the temperature up to 125 degree, starting from -55. The next series of device this is an LLC half bridge UCC 25800, and the input voltage range can vary from 9 to 34 volt. And again, the switching frequency, if you see, it is from 100 kilohertz to 1 megahertz of switching frequency the device can cover. So it's having two adjustable current limits. It's having settable OCPs, OCP1 and OCP2. And the device can work temperature up to 125 degree. So today we will be majorly discussing on SN6507. The device is having an input voltage which can go up to 36 volt input, and the switching frequency specifically can go up to 2 megahertz, starting from 100 kilohertz to 2 megahertz. And the device, if you see the device features, it's having a slew rate control and a spectrum clocking for a low EMI, the duty cycle control to compensate wide input variations, and the device having an adjustable soft start, right? The customer will be able to set the soft start programming. So the device having an external switching frequency programmable, as mentioned, from 100 kilohertz to 2 megahertz. And it's having internal protections like overcurrent, overvoltage, and thermal shutdown, which is integrated to the device. So if you see all these features, right, the device will have a low EMI compared to the previous generation SN6501 and 05 because of the spectrum, which is included in the device, and a lot of input protections which will help the device to protect from the multiple fault conditions. So the main highlighted features of SN6507, it's having a slew rate control and a spectrum clocking for low EMI emission. So we have test data which is available, right, according to CISPR 32. This is the graph which we have, which shows for a 24 volt input and a 15 volt output with a 500 milliampere load, the device actually is having better performance in CISPR 32 class B limits. And the device, next important feature for the device is the duty cycle control. It's having an output line regulation, right, which can maintain with duty cycle control. The output line regulation can be within 10% for the input variations ranging in different voltages. So we have an external pin which you will be able to set the duty cycle based on the variation requirement which you need to cover for the input voltage. So if you see the application circuits, the device can actually work, can generate a bipolar output for any type of gate driver applications, or if you want a higher voltage output from a device, it's a doubling output application, or you want to quadrupling the output, you will be able to do that as well from a normal push-pull applications. So the device can have wide range of application which it can cover. It can be a power supply for a drives applications, basically for the traction drives or motor drives, or even for the PLC communication systems, for medical applications. The device is having wide application range, which can generate any output voltage, bipolar output for any applications for an isolated 485 CAN or a traction driver applications. The device is having wide applications. If you see the key advantages and system benefits, higher power density, right? The device can have up to 7 watt of isolated power, right? Because it's very simple to use. It's a low system cost. The device is having very less external components to set the output voltage or the duty cycle or the frequency control. Because of the sweat spectrum, the device is having a controllable EMI, which the customer will be able to adjust according to the requirement. The system will have higher efficiency compared to any of the devices which is available in the market. Better line regulation, because the device is having the feature of duty cycle control. It will help to have a better line regulation. So programmable duty cycle, programmable switching frequency up to 2 megahertz, which will help the customer to use a very smaller transformer, which will actually reduce the power, reduce the total design area, as well as it increases the power density. Duty cycle control, which actually compensate for wide input variations. So it can give better line regulation, right? Which will be somewhere near to plus minus 5 to 6% with a smaller transformer. Slew rate control and spectrum, which contributes to the low EMI and which is easy to pass the CISPR32 standard with a lesser component count. Adjustable current limit, control over if customer want to set any current limits specifically for the limited applications, current limit applications, it will be able to set the current through a single resistor. Soft start, right, to avoid the large capacitive transient currents. So the device will have a adjustable soft start, which will able to help. External clocking feature, which will be able to synchronize multiple devices or with an external system to synchronize the clocking frequency for different applications. So for traction drive or the uninterrupted power source or the PLC or EV onboard chargers or external chargers, so the device goes well within the system for multiple applications. So we have different design resources and tools available online. So the technical documentations and data sheets will be available on the product folder. So we have a couple of evaluation modules which will be available. So for design tools and support, we have an IBS model file and a WebBench designer tool which is available online, which you will be able to use for the quick design. And we have a 24/7 E2E support forum, which will be able to answer the queries quickly whenever you started the design, a new design. So TI, a partnership with Wurth, we have multiple reference designs and EVMs which developed together specifically. If you see the TI EVM, the transformer is completely from Wurth, right? For the EVM, we have a joint development EVM from Wurth, as well as to demonstrate the capability of the device. We have a couple of reference designs which is in partnership with Wurth. We developed specifically for SN6507 and its related applications.
Thank you, Shinyo. So I'm Dean Umoa. So like Lelia said, I'm a product manager. I'm managing the team for Würth Electronics that does the isolated power products. So I am going to tell you a little bit about the history of these series of transformers, what we have, and how they developed, and how we got to where we are today. So if I share my screen here, hopefully you all can see this coming up about now. So the question is, does everybody see my screen? Can somebody? Yes, they're visible. Okay, very good. Thank you so much for that. So, like I said, I'm trying to now switch. Okay. So I want to talk a little bit about the development of the PPTI over the years. This really had its start back in 2011. I was there in Dallas for another meeting, and there was another TI colleague who wanted to visit with me. And so I was in this room, and in walks this big German man with a big smile and a big voice, and he had big plans. And so he started to tell me about this cool little IC they were developing, and this was the SN6501. And the cool thing about it was very, very simple. 7 to 10 parts, you could have an isolated power supply. And so our idea was this needed to be not only small and simple, but it needed to be cheap. And initially, he had talked about having a high isolated part with reinforced insulation and whatnot. And as we talked more about the applications and where it would go, well, that was a portion of the market. And at that time, the larger portion was really without reinforced, but more of just a functional type of design. But the whole idea was this was for CAN bus type of applications, or these little communication applications where you needed a little bit of isolated power to run these. And originally the thought was 170 milliamps, and then 100, kind of crept it up to 120. And we worked with that, we talked about it, and eventually we had said 150 milliamps was what we needed. And that was for both 5 volts and 3.3 volts, but began to find there's other applications that really would work. And the full power of the chip came out to be 350 milliamps, and the parts we designed, they were designed around that 350 milliamps, or that was the thought, had to meet at least that. And we were finding that these designs were going into a lot of other industrial automation type applications, and even medical equipment turned out to be a fairly big application for the higher isolated version. So, but what we had come out with first was our 1006 type. So it was very small, low cost, max height of 4.2 millimeters. And these were initially just 3.3 volt and 5 volt inputs, and then 3.3 volt and 5 volt outputs. And we had different versions, so you could use it with or without an LDO. You need the little bit of extra headroom to run the LDO if you want really precise output control. So later, as more and more people use this, we developed versions for 12 volt outputs, 15, 19, 24. So different output versions were added. And this was just a functional isolated part at 2500 volts AC. And later, when the 6505 came along, we began to push this part to its maximum, because it could handle more than 350 milliamps. And we found that some of the parts could go up to even 900 milliamps. So this was not only was the 6505 backwards compatible, but this was like forward compatible almost with the 6505 in some respects. So then after that, we developed what originally was asked for, which was a reinforced version. That's our 1209. So it's roughly the same footprint, but it is taller, and it's good for reinforced up to 800 volts RMS. So a lot of different applications. We have many different safety standards that we have either it's designed to meet, or we've actually got approvals on that. So you can always check our data sheets to figure out what that is. But this one as well was originally 350 milliamps, but in pushing this and using it in other, like the 6505 type applications, we found we could run that up to about 1.2 amps. So these were the first series that we came up with, and the German FAE that we were working with, he said this thing's going to be big. There's going to be a lot of people who want to use this, and he was right. This has been very, very popular. The 6501 and the subsequent series have been very, very popular, and we found people use them in more and more different applications in ways we would have never dreamed. So that brings us to the 6505. Quite quickly after the launch of the 6501, we began to realize that, you know, it doesn't quite cut it for how people are wanting to use this. We need more power. People love the simpleness, the low cost, the small size. So in 2013, we got together again with Texas Instruments and began to talk about the next version, which was the 6505. So this was backwards compatible with our transformers, so to speak. Our transformers would work with the 6505. You just had to make sure you stayed within the power limits of both the transformer and, of course, the IC in your whole circuit. But this had a much higher current limit. Rather than 350 milliamps, this was 1.7 amp output on this. It was also low EMI version was available with the 160 kilohertz, the 6505A, and in some applications they need very low EMI, and this was addressed with that. So we had two versions, the 6505B and the 6505A, which were both for higher output current, and also you had the option for low EMI. They also added a few more features to the chipset. There's an enable pin, there's thermal shutdown and short circuit protection, and you could synchronize the devices. So the applications were expanded with this. They became more suitable for some low noise isolated USB supplies, precision instruments, and things like that. So again, if you're looking to minimize emissions, you want the 6505A. Or if you want higher efficiency and smaller footprint, the 6505B is a good option where the 6505B is running at that 420 kilohertz. So around 400 kilohertz seems to be the sweet spot for these, but you do have to deal with a little higher emissions. So from our side then, we developed together with TI a couple of more series. So one, we developed a 1208, which was a little bit bigger than the original 1006, but it increased. So the 5-watt power, we could easily handle that, and we can get up to 1.2 amp output. So it started with 3.3 and 5 volt outputs, but later we added 12 and 17. And the max height was actually, we kept the max height the same as the previous version. Also, we added a supplementary version, which includes not only the 3.3 and 5 volts, but the 12, 20, and 23 volts. And again, it's designed to maximize the 6505 chip, and the height is in line with the other parts. So again, but quite small parts. Of course, it had to be extended a little bit to meet the supplementary. But the old, like the 6501 high voltage parts will work quite well with the 6505 and covers most applications. But when you run it at 160 kilohertz and your ET constant needs to be quite a bit larger, which results in a larger part, and that's where our 1512 part came in, where we have those for 3.3 and 5 volt inputs and outputs. And these have been used like where you have that, you want those low emissions and you have the high safety that you need. And we found those are often used also in those medical applications. About this, around this time, we found that we were testing so many different parts, so many eval boards with different parts that it took a long time in the lab. So we developed an automated test system to test temp rise of not only our transformer, but the IC and the diodes, so whatever's getting warm. And then we can automatically check efficiency and load regulation. So now every part we develop, before we release it, we actually test them out and make sure that they're going to work well in application. And often we end up tuning them a little bit to change the load regulation or whatnot. And this also is a service that a guy could do for a customer if it warranted it. But this gives us a very nice capability, and we found that later in the 6507, this turned out to be a very good feature to be able to, I mean, a good tool for us to use to be able to further the development of the 6507. So that was the third generation. Then some years went by where the 6505 and the 6501 were enough. When it came to people began to ask about higher input voltages, 12 volt inputs, 24 volt inputs, and we actually had some workarounds and we had some designs that would work with that, but they weren't as clean, they weren't as simple as the original 6501 and 6505. But back in 2019, around COVID time, I think you all remember that time. But anyway, about that time, again, we got together with Texas Instruments and began to work on that, on the 6507. And this was designed for a wide input compared to the other ones, 3 volts to 36 volts and 500 milliamp current limit on the IC. And this as well can be designed for low EMI if you run it at a lower switching frequency. As a switching frequency is 100 kilohertz to 2 megahertz. You can set it. I think the default is 1 megahertz. The thought was maybe a guy could get smaller parts for transformers running at 1 megahertz. But as we found out, it didn't work so terribly well at 1 megahertz. When we initially launched it and we finally got the chip. We got the chip produced and we tested it out. We began to test it out and we found that, well, the parts were running hot, not just our parts, but all parts that we had. So we're thankfully able to test the EBMs very quickly. As we had the automated test system, we were able to change parts, work with those, and adjust the design. So what we found was at 1 megahertz, they were actually getting uncomfortably hot. We didn't care for that, so we changed the designs. The sweet spot really is 400 kilohertz, and but they will run just fine at a megahertz as well. Our designs that are designed for the 6507. Now with the 6507, we're talking about a much higher ET constant again. So most of the prior parts aren't necessarily going to work with the 6507. Of course, it depends on what switching frequency you run it at. Running it at a little higher frequency, yes, some of them might work, but you got to watch that. It's not just a plug and play. You got to make sure you're taking care of that so you don't saturate the part. So this chip also added more features again over the second generation. You could adjust the UVLO, and it had overcurrent protection and some duty cycle and slew rate control on it, as well as, like Shin, you mentioned, the soft start and current limit functions on it. So it was, again, a step of more capability, and definitely the big thing though was the wider input range. And we saw, again, the applications open up more with this version. So what, for us, we've developed, we have like the 1308, again, small size, kind of compare, it's bigger than the other ones. It's got more ET constants, so you have to have a bigger core to handle it, but it's still very small, low cost. And we have both 12 volt and 24 volt input versions. Of course, you can use these same parts for other voltages as long as you're in other frequencies, as long as you're taking care of what's happening. So if you're looking at the ET constant. So these ones have outputs from 3.3 volts up to 30 volt, and are just the standard 2500 volt AC parts. And on this, we can push this up to about 7 watts on the, which is hence SN6507. And the max height also increased a little from roughly 4 to 5.5 millimeters. We also have a couple other versions. One is EPX6, and the other one is the EP7 high voltage reinforced version. Both of those are available in production units. They're not on our website yet, as we are running them through AEC Q200 at this moment. So the 1308 is already on the website. The other two are being run through AEC Q200. Once that passes, we will add them to the website. So the EPX6 is, again, it's small and low cost. It's roughly the same footprint as the 1308. Cost-wise, are roughly equivalent. The benefit to it is we can get more, about 50% more power out of it, and get about 10 watts out of that. So we really push the limits with that on that 6507 chip. And these, though, we have tested, and in our testing with the eval boards from TI, we've been able to run them there without anything getting too hot. So of course you end up with a larger part to get the more power, so it is a taller part. With the EP7 HD, we have again, we have many different outputs for the high voltage one, and they're designed for 500 volts reinforced. And again, they also can get about 10 watts, but these have an increased footprint and an increased height in order to get that reinforced insulation into the part. So now, also, I'd just like to mention, just like Shinyu did, we did a joint development on our development kit, and we have two different boards: the 650796 board, and then the 700 board. And the fixed board has a 24 volt to 15 volt design on it, so it's been tuned for that design. It meets all the CISPR 32 standards, so it's a very good board. It has very high efficiency, around 90% efficiency on that board. And then we have a configurable board as well. And the configurable board, with that, we have like 8, I believe, 8 to 16 transformers. It says 16, I thought it was 8, but there's a number of transformers in there for different outputs and inputs. So you can swap it out, change it, and the board can be used in many different applications. So both are excellent boards. Both are available. We have stock, I believe, on them. So if you're wanting to try it out, definitely the way to go. Both of them have very good efficiency and good for EMI, etc. So check them out. Those were co-developed and are available from us. So that is it. And now I think you can feel free to ask questions from either myself or from Shinu.
Yes, thank you very much, Shinu and Dean, for presenting. We did have some questions come in advance to our email, the webinar team at we-online.com. First up, Shinu, if you could sum up in one sentence why these devices should be chosen, what would it be?
Yeah, thank you for that question. Specifically, if you see, right, ETA is having wide customer support, I think, specifically in each and every regions. And we have a very wide, good application note specifically on this device with multiple reference designs, right? If you see for various system level applications or end equipment applications, we have different reference designs which is created specifically for those applications, and we have a 24/7 E2E that is engineer to engineer support forum, which is available where whenever you start a design, our application engineering team can come and support you. And moreover, TA is having 100% in-house manufacturing specifically for this type of devices, right? I think these are the points, right? I believe a customer will prefer to select a device right now.
And also, Shinu, why then would our followers or attendees, why would they choose Texas Instruments as a supplier?
See, specifically, I believe because of the device support which TI it provides to the E2E forum, engineer to engineer forum, that's a 24/7 online application support. And TI is having in-house manufacturing specifically for all analog devices, right? That is, I think, one of the major thing which TI gives, and multiple right partnership levels, right? Similar like Wurth or right, those things actually customer can specifically select these devices right whenever their application requirement comes in, right, so that they can quickly design according to the needs.
Excellent, thank you so much. We do have a few questions here, it looks like for Dean, specific to these transformers. Why are the Generation 2 reinforced transformers so much larger than the other ones?
Yeah, good question. Really, the reason is because of the frequency they're running at. The 6505B, it can use the Gen 1 reinforced transformer, but if you want to run it at 160 kilohertz for the 6505A, then your ET constant gets to be much larger. And in order to be able to keep that part from saturation, we have to build a larger transformer to support it. So that's the reason.
Thank you for that explanation. Another question here. Can I use an LDO to regulate the output with any of the IC and transformer options?
Absolutely, you can. The only thing you need to make sure is that you have enough headroom. So you don't have to just use the part that was designed for an LDO, but you can use any part. But depending on what output you want, you just make sure that you choose a turns ratio that gives you enough headroom so that you'll be able to maintain the output you're after. So yeah.
Thank you for that explanation. We have a couple more questions coming in here. Are this one, our bread and butter, are custom versions of the PPTI available?
They, yeah, they are available, but we have a whole lot of different turns ratios available, many different parts. Before I would ask for a custom, I would check with us if you are unable to find it, because most likely we have something that's going to work. Sometimes you can run these in reverse rather than forward. You just got to check ET constant, etc. But normally we have something available, and you have a benefit with the catalog versions. They're AEC-Q 200 approved already or qualified. And in many cases, we have safety standards, and of course, we have stock available. So I would say check first before you go down the custom route there. I see that in the chat. There's some other ones coming in.
Yes,
Here.
it looks like we do have time for one more question before we are reaching our marker here. Final question, and then we will be able to respond to these offline as well. This individual has been playing with the kit with 1512 transformer parts and medical applications. Their understanding is that the parts are not washable. And what wash process do you use?
Okay, so that's a general statement on all wire wound components, that they're not washable. Now, that being said, most parts get washed. The thing is, it's kind of like a covering your backside, so to say, a little bit, that we don't want to get bogged down into any legal stuff. But the reality is, most parts get washed. You just need to, if you're going to wash them, you got to make sure things dry out. You don't want to leave water in there forever, but there has to be some kind of good drying process. So we kind of covered ourselves with that statement, but there's other wash methods that can also be used with things that evaporate really well. But I would say, yeah, I can't go out and say, yeah, go ahead and wash it with water. But we're talking about water washing, and anytime you leave water in there over time, if it's left and trapped inside, it will eventually start to degrade the insulation, and over years, it could eventually, through the pinholes, cause that corrosion that happens with copper, and at some point it could short out. But if you dry it, it shouldn't be a problem at all.
We are out of time. Thank you, Shanu and Dean, for presenting today's webinar. We greatly appreciate it.
All right. Thank you, everybody, for attending. We really appreciate it.
All right. And thank you, everyone. As we mentioned before, if your question did not get answered, you can respond directly to our follow-up email, which will be sent within the next week from webinarteam@we-online.com. And then we will be responding to you directly after that. If you are looking for any upcoming events, we urge you to check out our website, www.we-online.com/webinars, for our future webinars, and we've already been planning for 2026. Thank you again for joining us today's joint webinar, Power Up Your Design, the SN6507 ready-to-use development kit, presented by Würth Elektronik and Texas Instruments. I'm your host, Amelia Thompson, and I hope to see you soon.